Dawn of history, mankind has revealed an unconquerable urge to improve his lot. Along with his requirements of food and shelter have been the deep-rooted desires to reduce drudgery and to move freely beyond the horizons of his limited domain. Time and space have always presented their challenge. Man early recognized that energy must be found, harnessed, and properly applied to help him. But throughout many centuries, man was unprepared to see the potential servant in a substance that occasionally seeped from the Earth's crust, oil. Oil has long been known to mankind. Aware of its unusual burning characteristics, the Babylonians dipped their ceremonial torches in oil and pitch. In drilling wells for water and brine, the Chinese came upon oil 600 years ago. Their energy and power facilities remained, however, limited and primitive. Little did they know that oil such as they encountered would someday be a source of freedom from toil and drudgery. Early American Indians used the oil that they found as a medicine and ointment. And even in the 1800s, petroleum, recovered as a nuisance byproduct of brine well drilling, was sold as a cure-all. But now the progress of civilization had set the stage for an awakened interest in petroleum. Animal fats and tallow could no longer supply the ever-growing need for candles and lubricants. Whale oil, which had long been the chief illuminant, was becoming scarce, yet the demand for artificial light was increasing. In 1850, a lamp capable of efficiently burning a refined product of petroleum was invented. Petroleum, it seemed, might supply the growing need for lubricants and light, but digging for it at seeps could not supply it in sufficient quantities. The fact that some oil had been found while drilling brine wells suggested the interesting possibility of drilling for oil itself. In 1859, a derrick was constructed near oil seeps at Titusville, Pennsylvania. This was accomplished under the direction of a retired railroad conductor, Edwin L. Drake. With the assistance of an experienced brine well driller, Uncle Billy Smith, operations finally got underway. Crude handmade tools and a primitive steam engine enabled them to drill at a rate of only 3 feet per day. A depth of 69.5 feet had been attained with no encouraging signs when one Sunday morning, Uncle Billy took a look around. Thus, on that eventful day of August 27th, 1859, Edwin Drake and his associates ushered in a new era. It had now been shown that oil in substantial quantities could be obtained by drilling. With the rapid spread of the news came a fantastic migration of those who saw in this development a possible source of new wealth. The boom was on. Towns and derricks sprang up almost overnight in the vicinity of Drake's discovery. For lack of engines and drilling equipment, many crude but ingenious drilling methods were devised. Strong backs and legs and infinite patience supplied the power to drill only a few feet per day. With the realization that many drillings resulted in expensive and disappointing dry holes, so-called experts with divining rods, luck, and intuition were much in demand. Yet the combined efforts of these pioneers resulted in rapidly increasing oil production. Waiting for slow and inadequate transportation, oil piled up at the well sites. Storage became a vital problem. Anything that could hold oil was pressed into service. Thousands of wagons and teams became regularly engaged in hauling the oil to the nearest shipping points. When possible, barges and rafts were employed to carry the oil. Such transportation proved inadequate in supplying the fast-growing market. And so in 1865, the first oil pipeline was laid over a 5-mile distance from Pithole City to the railroad. Within 9 years, a 60-mile trunk line of 4-inch pipe stretched from the oil region to Pittsburgh. Seeing the rapid loss of their revenue to the successful pipelines, the teamsters fought hard and bitterly. But they could not stop the growing momentum of the industry's progress. Crude refining plants, or stills, boiled and separated the oil into the two items in demand: kerosene for illumination and heavy lubricants. An undesired product, considered dangerous and unusable, was discarded in great quantities. The product was gasoline, the very portion of crude oil that was soon to change the economic and social status of the industry and the country. These refineries were, however, supplying illumination and heat for many homes, and through lubricants were freeing the wheels of a fast-growing industrial machine age. At the turn of the century, a momentous change in the course of the industry was in the offing. The use of oil for light seemed doomed to rapid oblivion. At this critical stage appeared the invention that was to revolutionize the oil industry's course of progress and change the living habits of the nation. No longer was gasoline destined to be a useless byproduct. Instead, with the swift popularity of the automobile, gasoline quickly assumed the position of prime demand. With the development of the internal combustion engine, a long unrecognized potential use of oil had at last been revealed to mankind. The recognition of oil as an economical and easily handled liquid source of power was the springboard for a new era of magnificent progress. Inspired by the American system of possible reward for risk, discovery and expansion swept westward to the Pacific, the mid-continent, the Gulf Coast, and the Rocky Mountains. The oil industry quickly found its stride in the suddenly stepped-up tempo of progress. With ever-increasing and improving oil products, it kept pace with invention and even forced it to proceed at a rapid rate. Through enterprise and the accumulation of knowledge, it has now reached a stage of maturity undreamed of even a generation ago. Throughout millions of years since the Earth's formation, constant heaving, buckling, and erosion have changed many portions of the Earth's surface. Many areas were repeatedly covered by shallow seas. Countless billions of tiny organisms died and settled to the bottom, where they became buried under sand and silt. There, it is believed, the entombed organisms were transformed into oil. Accumulated pressures of gases, water, and earth sometimes drove the oil through the porous sand and sedimentary rock. And often, it migrated to underground reservoirs sealed by non-porous formations where the oil was trapped. It is from these reservoirs that oil is now most likely to be recovered in commercial quantities. Thus, today, the oil geologist searches both for locations where oil may have been formed and locations where oil may have been trapped. Conditions that were favorable to the formation of oil may be indicated by traces of ancient seas and fossilized remains of long extinct organic material. Underground formations where oil may have been trapped may be indicated by surface structures. Stereoscopic photographs are a great aid in the study of surface indications. Another method of search for oil is through chemical analysis of soil samples for minute evidence of seepage of the lightest hydrocarbons. The economy of this method permits blanketing large areas, and promising indications are then verified by more expensive detailed geophysical methods. In the far-flung search for oil, modern geologists and geophysicists often make use of the helicopter and the marsh buggy, a special vehicle which can take them into almost inaccessible swampland. Subterranean oil traps may be found by mapping underground formations. The gravity-meter gives clues to the nature and depth of these formations by measuring the gravitational pull. The magnetometer is another instrument that can help plot underground formations by measurement of the Earth's magnetic fields. One of the most important of all methods of search is the seismograph. A shallow hole is drilled for a small explosive charge, and special microphones are strategically placed around the shot. The detectors will pick up the explosion and the shock waves reflected from far underground. This will give information as to the shape and depth of the underground strata. The shock waves are reflected by the various rock layers underground and are recorded at the surface. The time it takes for the waves to make this round trip varies with the distance they travel. The recorded measurement of this time lapse indicates the depth. Thus, through a series of shots, the shape and depth of underground formations are mapped with accuracy. The seismograph is even used to detect potential drilling sites several miles out at sea. Special sensitive geophones are lowered into the water to predetermine depths and positions. Explosives are detonated under the water. As on the land, the recordings of reflected shock waves reveal variations in the ground strata under the seabed. Actual drilling is still the only conclusive step in finding oil. Even today, in new field drilling, only about 1 well in 9 becomes a producer. Costs of drilling a well will average about $77,000, but some wells have cost as much as $1 million. The older cable tool method is still generally used in drilling formations hard enough to stand up well and where low cost rather than speed is the principal consideration. The rotary drilling method, developed since the turn of the century, is now used more extensively. Although more expensive, it is speedier and enables drilling through loose, unconsolidated formations to far greater depths. In drilling to depths of 2 or even 3 miles, the repeated raising, lowering, and handling of the drill pipe to replace the bits is a difficult, time-consuming function. Steel pipe, or casing, is used to line the well walls and give them strength to prevent caving in of the hole. Cement, pumped around successive strings of casing, seals the holes against leakage of oil, gas, or water. As the drill passes through various types of formations, weight on the drill bit must be suitably adjusted. This retards wandering of the drill from its course and possible buckling or bending from the accumulating weight of added drill pipe. Chemically treated muds are pumped through the hollow drill pipe to cool and lubricate the bit and carry the rock cut away by the drill back to the surface. It also plasters the walls of the hole to help prevent cave-ins. A screening device called a shaker removes the rock particles from the mud, preparing it for reuse. Samples of the cuttings are examined to determine the kind of strata being drilled through. Even the senses of taste and smell are used as an occasional quick test when it is suspected that oil-bearing formations are being approached. Core samples are taken with a special drill bit at some drilling locations. These are sent to field and central laboratories, which test them for porosity, or the volume of small cavities that may contain oil, permeability, or the potential rate of flow through the rock pores, and the oil content of the sample. Still another method of estimating underground conditions is through measurement of electrical resistances at various drilling depths. This process is known as electric logging. During the process of drilling, a special valve at the top of the hole may be closed off in the event of unexpected blowouts. When an oil-bearing formation is reached, the drill is pulled. Heavy muds are used to hold back the flow of oil from natural pressures. Wells are no longer permitted to blow in as dangerous, wasteful gushers. A final string of casing is set. Some wells are shot with explosives, permitting the oil to flow into the well. When the glass-enclosed charges of this perforator are detonated in the hole, powerful jet explosions penetrate the casing and surrounding rock. A small diameter tubing through which the oil will come to the surface is installed. At the surface, a system of valves called a Christmas tree is installed. This controls the flow of oil. Sometimes wells are treated with chemicals or acidized to open up passages in the limestone for the oil to flow through. Other chemicals may be used to stimulate oil flow and prevent water migration to the well. When natural bottom hole pressures are not enough to force the oil to the surface, the well is put on the pump. In many locations, ingenious centralized power systems work a number of well pumps, bringing the oil to the surface and sending it to the storage tanks. In the present-day application of scientific production methods, the industry is wisely trying to conserve reservoir energy by maintaining subsurface pressures. No longer are wells drilled without regard for adequate spacing. The production of individual wells is carefully regulated to prevent waste or depletion of reservoir energy. However, in many fields, reservoir pressures have been lowered to a point where oil does not flow naturally to the wells. In many such locations, natural gas, usually associated with oil production, is first piped to cycling plants where liquid products are extracted. The gas is then pumped into the oil-producing zones, where the pressure helps the oil to flow through the sands and porous rock toward the wells. In other locations, water instead of gas is employed to drive the oil. These are a few of the many ways in which oil is now recovered that would otherwise have been lost forever. Oil production on land has been augmented in recent years through drilling at sea. Oil producers are thus opening vast new production potentials to bring more oil to the nation.